Case analysis. Our first speaker of the day will be Uri Feige, a professor at the Weizmann Institute. He'll talk about universal factor graphs.
So good morning. This is a joint work with my PhD student from Weizmann, Shlomo Joseph. So we all know what constraint satisfaction problems are, but here's a small reminder. In our problems, in constraint satisfaction problems, we'll denote the number of variables by n, and we'll have m constraints. The constraints are sometimes called clauses or factors. They come in different names. Each constraint involves several literals, and one needs to find an assignment that satisfies all constraints. As a well-known example of a constraint satisfaction problem, we have the problem of 3-SAT, in which the constraints, each constraint contains 3 literals, and a constraint is satisfied if at least one of the literals is set to true. And as is well known, many of the constraint satisfaction problems are NP-hard. A factor graph is a graph that is associated with a constraint satisfaction problem. On the left-hand side, we have the constraints or the clauses or the factors. On the right-hand side, we have the variables, and it's a bipartite graph connecting variables to constraints. So for example, variable x4, the fourth variable appears in the third constraint and in the second constraint, so we have edges connecting the variables to the constraints. We can add additional information to the factor graph by labeling the edges depending on whether the corresponding variable is negated in the constraint or not negated, as in the example here. So x3 is negated in the third clause, so we color this edge red. So this is a factor graph plus polarity information. So for symmetric predicates, these are predicates that in each clause only count how many literals are set to true. Examples for that would be SAT, XOR-SAT, AND, majority, not all equal. For these predicates, once you see the factor graph and the polarity information, you completely know what the instance is. That's the whole information that you need. For predicates that are not symmetric, you may need additional information to exactly characterize what the problem is, but for symmetric predicates, this is enough. So in this talk, we'll concentrate only on symmetric predicates, and all variables are assumed to be Boolean in this talk. Much of what I will say can be generalized to other settings. So what is the research question that motivates this talk? So we know that this problem, constraint satisfaction problems, are NP-hard, and what are the obstacles for what makes them NP-hard? Why are they difficult? So one reason might be it's because they are really, in some sense, a graph problem. That the algorithms that try to solve constraint satisfaction problems do not really understand the structure of the underlying factor graph, and this causes some problem for them, and for this reason they cannot solve the underlying constraint satisfaction problem. But on the other hand, maybe it's not really the graph what's causing the problem, it's just the richness in all possibilities for the polarities of the variable. This causes various interesting combinatorial structures, and this is what the algorithms cannot understand. So we do know that the structure of the factor graph does matter, in the sense that if the factor graph is very simple, let's say a tree, then essentially all constraint satisfaction problems are solvable in polynomial time over this class of factor graphs. And this generalizes also to other families of graphs. So the factor graphs do matter. Now let's just look at another variation on NP-hardness. This is approximation problems. So these are optimization versions of constraint satisfaction problems. And the goal is, given a constraint satisfaction problem, to satisfy as many clauses as possible. Find an assignment that satisfies as many clauses as possible. In general, this is NP-hard, and this is NP-hard even for constraint satisfaction problems such as 2SAT, which are solvable in polynomial time. Just the decision problem whether everything is satisfiable you can solve in polynomial time. The optimization problem is still NP-hard in the case that they are not satisfiable. To know to which extent they are not satisfiable is NP-hard. Moreover, for many constraint satisfaction problems, we have NP-hardness of approximation results, the most celebrated one by Hastad. For example, we know that we cannot approximate max 3SAT within a ratio better than 7/8 unless P equals NP, and to approximate it within a ratio of 7/8 is easy. So that's the exact threshold. And in general, under a certain conjecture known as the unique games conjecture, in fact, for essentially all constraint satisfaction problems, we know what the optimal algorithm is in terms of achieving the worst case approximation ratio. It's some sort of a semi-definite program. We don't know what approximation ratio it gives, but we know that whatever it gives, that's the best that you can do under the unique games conjecture. So the situation with respect to approximability of constraint satisfaction problems is quite well understood. So also for constraint satisfaction problems, we can ask the same kind of question. For the optimization versions, we can ask the same kind of question. Is the problem in getting good approximation that of understanding the structure of the factor graph, or is it like the polarities who cause the problem? And also here, for certain simple families of factor graphs, such as planar factor graphs, we know how to achieve much better approximation ratios than we know for the most general case of factor graphs. On the other hand, for certain constraint satisfaction problems, there are certain families of factor graphs that appear to be difficult. So if you look at random 3CNF formulas, so the problem is 3SAT, and we just take random factor graphs at certain densities, some high enough density, then for such formulas, like for such, if we pick a formula at random, in general we don't have algorithms we don't have any polynomial time approximation algorithm that on these particular formulas gives an approximation ratio better than 7/8. So it could be that if we just take a factor graph at random, maybe already the instances that you can have on this factor graph by just varying the polarities of the variable. So in general, for every factor graph, there are 2 to the n possible instances, depending on the polarities of the variables, or 2 to the 3m. If m, each literal, you can change its polarity. Then it could be just that if you just take a random factor graph and vary the polarities, this already is hard to approximate within a ratio of 7/8. On the other hand, if we look at the unique games conjecture that we mentioned earlier, if we take there a random factor graph, usually in the unique games people look at a related graph, which is not the factor graph, it's the constraint graph, but there's a one-to-one correspondence between these two graphs. If we look at random factor graphs or random constraints graphs for instances of unique games, these are not difficult. They are still NP-hard, but we have very good approximation ratios on them, much better than what the unique games conjecture would deem to be difficult. So we can ask ourselves, let's say, which are the factor graphs or constraints graph on which the unique games are difficult, on which they are difficult. So there are additional easy factor graphs for the unique games. There are other families of graphs for which it's easy. There was an earlier paper by Luca Trevisan. There are a generalization of, let's say, expander graphs studied by Kola, for which it was shown that unique games are easy. So should we continue this study of finding additional graphs on which unique games are easy? Like, what's the point of doing so? So one point of doing so is perhaps we can identify eventually one graph, such that if on this particular graph we manage to determine that unique games are easy on this particular graph, then in fact unique games are easy everywhere. That this factor graph is in a sense universal. Whatever you can do on this graph, you can do on any factor graph. If so, maybe we'd also like this graph to have a nice structure that we can understand, and some candidates would be some variations on graphs which are known as Knesser graphs. But that's a more distant goal, maybe. So now we reach to this notion of a universal factor graph. So this is like an intuitive level definition. So for a given constraint satisfaction problem, we say that a factor graph is universal if whatever performance we can have on this particular factor graph, and the performance depends on what we are interested in. If you are interested in the decision problem, then the performance is simply can you tell whether the instance is satisfiable or not. If you are interested in approximation ratios, so it's the approximation ratio you can get. If you are interested in running time for exponential time algorithms, then this would be the performance that we are interested in. So whatever performance you have on this particular factor graph, and you should have it on all possible polarities of the variables, you'd have similar performance, perhaps up to some negligible factors, on all factor graphs. That this particular factor graph captures the difficulty of the problem. So there are some technicalities involved with this definition. So it's really not just one graph. It's a family of universal factor graphs, which you can parameterize by the size of inputs. So let's say if n is the number of variables and m is the number of constraints, you can, let's say, for every combination of n and m, have a factor graph which is universal for this particular combination, and this particular factor graph need not have by itself n variables and m constraints. It may have somewhat more than n variables and somewhat more than m constraints. So here are concrete questions that we can ask regarding factor graphs. So does 3-SAT have universal factor graphs? Is there a particular graph or family of graphs, one for each input size, such that if you can solve 3-SAT on this graph, you can solve in polynomial time, you can solve it on any factor graph. We can then go one step beyond and look at approximation ratios. So for example, is there a particular graph such that if you have a PTAS, a polynomial time approximation scheme on this particular graph for 3-SAT, you have it for every factor graph for 3-SAT. Or you can just maybe try just to beat the threshold of 7/8. Is there a particular factor graph for which if you can, on this factor graph, instances on this factor graph alone, get approximation ratios better than 7/8, you can do it for all instances. We can have more long-range goals. We can ask in general, do all CSPs have universal factor graphs? Or the other direction of the questions, which CSPs do not have universal factor graphs? And perhaps the most interesting direction, if it ever works out, is to understand the structure of these universal factor graphs. If they exist, how do they look like? Can we find some simple-looking factor graphs that we can really understand? And once, if we reach such a situation, this can help us both in designing algorithms for these problems and improving hardness results, because we won't need to kind of each time think about like how does the instance look like. We know things about how the instance looks like. Okay, so these types of question in this particular formulation may be new, but in a strongly related formulation they were studied before in other contexts. And this is the context of NP with preprocessing. Since we are thinking of a universal factor graph as something fixed, and only if the polarities are changing, we may think of an algorithm that is given exponential time or infinite time, we don't care how much, in pre-processing the factor graph before the polarities of the variables, doing that in advance, writing down a short advice or designing a short circuit that once a small circuit, polynomial size, such that once we fix the polarities, we feed these polarities into the circuit, and then, or into our algorithm, and then this algorithm with the additional advice can solve the problem. So this is NP with preprocessing. It relates to the class P/poly, not exactly the same. So this is something that we can do here. Once we think of a notion of a universal factor graph, it's known in advance. So you can tailor the algorithm to this particular factor graph, and you can spend exponential time in designing the algorithms that fit this particular factor graph. So there was previous work on problems in NP with preprocessing. The first work I'm aware of is by Brook and Naor. They looked at the nearest codeword problem. It was previously known that the nearest codeword problem is NP-hard in the fact that if you get a code and you get a certain word and you ask what's the codeword closest distant to this word, this is NP-hard. But as Brook and Naor explained, this is not the situation usually in coding theory. Usually in coding theory you have the code in advance, and when you get a word with error that you want to decode, this is the nearest codeword problem. You can do that after you pre-processed your code for a long time and you know a lot of things about it already. It's not that you get a fresh code each time. So you are allowed to pre-process the code. The same kind of problems were studied for nearest lattice-vector problems with preprocessing. For example, there were some cryptographic schemes based on problems of that sort. And in these cases, the lattice is given in advance, and the message has something to do with a nearest codeword problem, but you can't pre-process the lattice for a very long time before you answer queries on it. And there were some hardness of approximation results for these problems. And in the process of proving hardness of approximation results for these problems, coding problems with preprocessing and lattice problem with preprocessing, people proved also additional hardness of approximation results for other problems with preprocessing as a tool towards these results. So is it plausible that preprocessing helps at all? And for lattice problem, the answer is certainly yes. So there was main motivation for doing these things. It is known that if you change the input basis of a lattice to a so-called reduced basis, the approximation ratios for problems like closest vector problem improve dramatically. But doing this change of basis, people don't know how to do it in polynomial time. But if you have preprocessing, you can do it in exponential time and then have a much better approximation ratio on closest vector problem instances. So preprocessing can help in these contexts. So what about preprocessing for constraint satisfaction problems? So here the situation is less clear, and all I have is some sort of mild evidence from work on random constraint satisfaction problems indicating that preprocessing the factor graph may help. So it would be only one slide. So it is known that if you have a random 3CNF formula that has a lot of clauses, more than n to the 3/2 clauses, and it's random, then there is some refutation algorithm that on these formulas manages to prove that they are not satisfiable and do so in polynomial time. So this is known. So random 3CNF formulas, if they are dense enough, are not that difficult. Now, if we want to extend it to a lower density, not n to the 3/2 clauses, but a smaller number of clauses, let's say n to the 1.4 clauses, the only obstacle to extending these results is only graph theoretic. It's only understanding the factor graphs of these formulas. These formulas should have certain substructures that are called even covers in them. I will not go into what they are. If you could find these even covers in the factor graphs, you'd be able to refute random formulas. The problem is only in finding them. That's the only problem. So if you could preprocess the factor graph and find these even covers, give them as advice to your algorithm, you could refute random 3CNF formulas. Moreover, work suggests that the following conjecture is reasonable. That in fact, this is not just a property of random factor graphs. For every factor graph of a 3CNF formula that contains more than n to the 1.4 clauses, the same thing would work. If you'd be able to do pre-processing, write certain advice, and then when you get the polarities of the variables, if the polarities are random, you'd be able to refute, to prove that this formula is not satisfiable. So in fact, like the obstacle to obtaining better algorithms in a certain regime is just graph theoretic. So this is the conjecture, and in fact this conjecture is true, and in fact something stronger is true once you have many more clauses. Once you go beyond n to the 1.5 times square root log n, then in fact you don't even need the preprocessing. For every factor graph that you get, if the polarities are random, you can refute the formula. Okay, so this is some indication that maybe something in the structure of the factor graph sometimes makes the problem difficult, and it's not just the polarities. So what results are known on universal factor graphs? So this is implicit in previous work on the closest vector problems, that for some predicates, such as satisfying quadratic equations, max optimization versions of constraint satisfaction problems have universal factor graphs. In the sense that if you have a pitas on these factor graphs, you have on every factor graph. So what do we do? So I think part of what we do is just suggest this as a research agenda. I think this is an interesting direction. As I said, previous work already dealt with NP with preprocessing, but there the motivation was somewhat different. It was really because practically this was relevant in these cases. Like in cryptographic situation, that's really what would happen. You'd get first, let's say, the lattice, then you'd be able to do preprocessing, and then only you'd get some code words. An aspect in which we deviate from previous work is that we attempt to get the best possible hardness of approximation result, not just APX hardness. This was attempted for these specific problems in coding and lattice problems, but not in general. And in terms of actual results, we managed to achieve nearly tight results for some constraint satisfaction problems. Okay, so now what I'll do, I'll describe some of the results that we have. So as a warm-up, let's just show that 3SAT has universal factor graphs in the sense that if you can solve instances of 3SAT on these particular graphs, you can solve them on every factor graph. So what is needed? We need to design a universal factor graph for 3CNF formulas that have n variables and any number of clauses. That's what we're going to do. So for each value of n, we'd have a different factor graph. For simplicity in this presentation, it's not really important. We assume that variables in a clause need not be distinct. You can have a clause that looks like x1 or x1 or x2. That's fine. And no two clauses share the same sequence of variables. So you cannot have two clauses like this, but just with different polarities. This just simplifies the presentation. So here's how to construct universal 3CNF formulas. Here's one way of doing it. So let's write down all n-cubed possible clauses under the convention that I described before. There are n-cubed possible triples of sequence of three variables that can appear in a clause. And then let's replace each clause by two clauses by introducing one auxiliary variable. So each clause Ci would have an auxiliary variable Zi associated with this particular clause. For example, the clause x1 or x2 or x3 would be broken into two clauses, x1 or x2 or Zi, if it's clause Ci, and x3 or Zi or Zi. Zi appears twice in the second clause. So this way we'll get a formula with n plus n cubed variables, the n original variables and the n cubed auxiliary variables, and we'll have two n cubed clauses. We doubled the number of clauses. And we claim that this formula is in a sense universal. So what does it mean? That every 3CNF instance with n variables can be embedded in this formula by appropriately setting only the polarities of the variables. So think of it, let's say you have a clause like that does not appear in the formula, like x, let's say x1 or x2 or x3 did not appear in the formula, f, in small f, then in our universal formula, we'll just set the polarity of zi, the corresponding zi to true in both instances. So now these pair of clauses are satisfied just by giving zi the value of true. On the other hand, if the clause, let's say x1 or not x2 or x3, does appear in the formula, the original formula, then in f, we just copy its polarities to the right locations, and in one of the clauses that we introduce, we will put z1 as false, as negated, and in the other we put it in positive polarity. And it's easy to see that any assignment that satisfies the original clause can be made to satisfy the two new clauses by setting the value of z1 appropriately and vice versa. So the factor graph that of this particular formula that we described now, that had two n cubed clauses and more than n cubed variables, is universal in the sense that I described before. So the theorem for 3SAT, there is a factor graph with order n cubed variables that is universal with respect to 3CNF formulas that have n variables. So this is not completely satisfactory, because think of, let's say, the original 3CNF formula, even if it had only, let's say, n clauses, we still constructed an object of size n cubed. That's not very satisfying. Also, it's not a good universal factor graph for other questions that we may want to ask about algorithms for 3SAT. For example, because we did have this huge blow-up, it doesn't exclude the possibility that on these factor graphs we can have algorithms that run in time, or maybe every factor graph, once we are allowed preprocessing, in sub-exponential time, significantly sub-exponential time, to the cube root of n maybe. And we'd like to exclude such possibilities. We'd like to say that there are also factor graphs in which the running times of algorithms, even if you're allowed preprocessing before, you cannot get a good speed up in running time. So we can have an improved theorem. So if we have a 3SAT formula which has n clauses and n variables and m clauses, we can construct a factor graph with m times polylog variables. And this factor graph would be universal. And this, assuming that when m is linear in n, currently we have no idea how to achieve sub-exponential algorithms. This implies that also for these universal factor graphs, you would not expect to have significantly sub-exponential time algorithms. So preprocessing would not save you a lot in the running time at the time that you get also the polarities of the variables. So ideally, we would like even tighter relation between this capital N and small n, but this is still open. Another question that we want to ask ourselves is APX hard, yes.
How does that graph look like?
So the graph of this, okay, it's based on the AKS sorting network. So in it, it includes the sorting networks. It's based on first encoding the names of variables in binary and sorting things and comparing. So if you know how the AKS sorting networks look like, you have a good idea of the structure of this graph. Okay. So if we look at previous work on lattice problems with preprocessing, a theorem of the form stated here was not explicitly proved there, but it's not difficult to derive it from there. That for some epsilon, there is a universal factor graph for 3CNF or 3SAT, with respect to which, once you give the polarities of the variables, it's NP hard to distinguish between satisfiable instances and instances that are not 1 minus epsilon satisfiable. So this follows from previous work. How does the proof go? Okay, so this was only a conference version paper. The proofs don't really appear in that conference version, so we are not exactly sure how they go. But later developments after that paper, there was Uri Feige's proof of the PCP theorem that makes it easier to argue about PCP constructions. So we provided an alternative proof, a proof that they could not have had because at that time Feige's proof was not known, which is based on an adaptation of a variation on Feige's proof as explained by Radhakrishnan and Sudan. And what it does, Feige's proof works by successive amplification of the gap, and we do the same thing. So technically, what do we need to show? We need to show the following, that if you're giving two CNF formulas which have the same factor graph G, but they have different polarities, if we apply Feige's amplification technique, then we'll get two new CNF formulas that again have the same factor graph as each other. So this is not exactly true for Feige's proof as written, but her proof can be modified to show something like that. So that's the technical content of our proof. So now let's go one step. So this is more or less where previous work on preprocessing would stop, because from this kind of statement, you can do reductions to lattice problems without worrying what's the exact hardness of approximation ratio that you get for problems like 3SAT. So now here's additional stuff that was not mirrored in previous work. We want to get tight results now. So here's a question. Is it true that for every epsilon, there is a universal factor graph for 3CNF or 3SAT, with respect to which it is NP hard to distinguish between satisfiable instances and those which are 7, 8 plus epsilon satisfiable? So that's the best hardness result known without processing. Is it also true with preprocessing? And the natural approach is to try to do what we did before. Look at the proof that we already know, Hastat's proof of the 7/8 hardness of approximation result, and see what happens. So what is the technical requirement? We'd like to show the following, that given two 3CNF formulas with the same factor graph G, but different variable polarities, does Hastad reduction produce two new CNF formulas with the same factor graph G prime now? So the answer is no, okay, that makes it more interesting. So is there an easy fix to this? So the answer, we don't know. Maybe, but we don't know. We haven't found it yet. So let me explain where the problem is. So this is a bit technical, but not too technical. So how does one prove tight hardness of approximation results using today's technology? So they're all based first on the PCP theorem, but this we already have the corresponding theorem in the universal setting. And in addition, they use what is known as the long code, which was introduced by Bellari, Goldreich, and Sudan. And the long code has some very nice properties. When a prover is required to write the long code, and you do some checks to verify that this is indeed a long code. So there are certain properties that a long code should hold that you can test for. And in addition, you want it to be the long code of an assignment that satisfies your instance. And the nice thing about the long code is that this is something that you never test, actually. You never explicitly need to test it if you're using the long code. There are various techniques called folding and conditioning that allows you to implicitly assume that the long code satisfies the predicates that you want them it to satisfy. You don't need to actually test for it. So I'll say a bit more about it in a minute, but more about the problem. So these folding and conditioning that are done on the long code depend on the polarities of variables in the underlying clauses. And if you change the polarities, what they do, they ask you to query other different locations in the long code, completely different locations. The locations that you need to query depend on the polarities. And as a consequence, when we do reductions that use the long code, even if you started with two instances which had the same factor graph but only different polarities, you end up querying different locations in the long code, which corresponds to getting different factor graphs after the reduction. So let me give an example. So if you've never seen the long code, it might be too much. If you know everything, this is maybe too little. But maybe for some people in the middle ground, this would be useful. So the long code of two variables. So if you have two variables, you can think of it as a 2-bit word, the value of one variable and the value of the other. The long code of this, or let's say of an n variables, would be of length 2 to the 2 to the n. So of 2 would be 2 to the 2 to the 2, which is 16. So how do we build this? So each code word would be of length 16. There are 4 possible code words in the long code, one for each possible assignment of the 2-bit word, and they are listed in these red rows. These are the code words for the 4 possible words. These are the 4 possible code words of the long code. And how did we design them? So we wrote down in the columns all possible truth tables. So like all possible binary strings of length 4, and just concatenated them. And this gives the 4 possible code words. So we have 60 new variables that are encoding the original 2 variables. So the value of the original 2 variables could be arbitrary. Any 2 setting of the 2 variables is okay. For the 16 new variables, there are only 4 possible settings for them which form legal code words, and all others are illegal code words. So what does folding mean? So let's say that these variables, the 2 variables that we had, are really variables x1 and x2 in a clause that said x1 or x2. So we know that if the clause has to be satisfied, then at least one of them has to be set to 1. So the truth table for them is like 0, 1, 1, 1. They cannot both be 0. That's why there's 0 in the first location. And at least one of them are 1, or both of them are 1. So if we know that we have a long code of a satisfying assignment, so it has to be one of these 3 long codes. It's not allowed to be this long code because that's not a satisfying assignment. 0, 0 does not satisfy the clause. Then we know that if, let's say, we look at these 2 green columns, they have to be exactly the negation of each other, because the functions that they represent, like this should be all 1 here, and this should be all 0 here. If this is one of these 3 true long codes. If this is a long code of something that does not correspond to satisfying assignment, then they are not negations of each other. But if it does correspond to satisfying assignment, then it is a negation of each other. So rather than try to check whether they are a negation of each other, like when we want to read a certain bit, let's say if we want to read this bit, we can force it to be the negation of this bit simply by just reading this bit and flipping it and imagining that that's what's written here. So rather than querying every possible location in the long code, you can like pair them together and say, I am going to read, let's say, if I want to read one of these 2 locations, I'll always read this location, and when I want the answer here, I'll just flip it. Okay? So this is the operation of folding, and forces that whatever written here, if it is indeed a long code, then it has to be one of these three long codes, but not that long code. So in addition, the PCP construction, the hardness of approximation construction, would need in addition to have additional tests to test that this is really a long code. That's a separate issue. But the issue of whether it satisfies the predicate is never tested. It's just this folding operation does it for you for free. That's why it's so efficient. You don't need to test for it, and that's why you get tight hardness of approximation results. Now, what would happen if we do folding over the same clause as before, just negate one of the variables? In this case, you get that these three are the legitimate long codes, and this is not legitimate anymore. And it's not true anymore that this column that we had before, the 8th column, is the flip of this column. Now it's the 5th column. You have to XOR with a different truth table. So now, instead of reading column 16, you don't read column 9, you read column 5. So what locations in the long code you read depend on the polarities of the variables. Okay, so that's the problem. So the problem is that the long code test involves the value, in this particular example, if you want to read the value of variable 16, if the predicate was x1 or x2, you read column 9. If the predicate was x1 or not x2, you read column 5. So you read something completely different. You read different locations, these are different variables, this is a different factor graph. So changing the polarities of the original formula changes the factor graph of the resulting formula. So this is the problem. So is folding hopeless? Can we, once we introduce the long code, are we lost? So not quite, because there are some special cases of folding that we can still do and still maintain the pattern of queries that we want, and we call these oblivious foldings. So there are two classes of foldings that we view as oblivious. One is something that is known as folding over true, so over the truth table 1, 1, 1, 1, where you complement everything. So let's say the two green columns are a complement of each other. So this is a kind of folding that is always done on the long code in all these PCP constructions. And it's independent of the predicate. So you can always do it. The other is more subtle. Sometimes we have complementary pairs of functions. Let's say NAND and AND are complementary in the sense that one is the negation of the other. So let's say that under some polarities of the variables you wanted to fold over AND, and under a different polarity you wanted to fold over NAND. So even though it seems that you would need to read different location, because we also do folding over true, and because there are negations of each other, it works out. You can do it while reading the same location and just flipping the answers. So you can do it. So in some special cases where changing the polarities of variables, changing the locations that you want to query in some a nice way that has to do with the folding over true, you can still do it. So what do we prove? So using this, we can prove that for every epsilon greater than 0, even with preprocessing, it's NP hard to distinguish between satisfiable instances or those which are 77 over 80 satisfiable. So we'd like 7 over 8, but this is 77 over 80. A few more details on the proof. So it follows the proof given in Bellari, Goldreich, and Sudan, which also gave exactly the same ratio, 77 over 80. But the folding done in that original paper was not oblivious in the sense that we described here, and we show that it can be modified such that all foldings that you need to do in the proof are oblivious, and hence the proof still goes through. If we try to look at Hastad's proof, he's using something, I'll not describe it here, which is more a bit, it's not exactly folding, it's called conditioning, it's a variation on folding, and we don't know how to make it oblivious. So we cannot use the same approach, or we didn't find yet a way of using the same approach in order to get a 7/8 hardness result. So are tight results possible at all? For 3SAT, we didn't manage to prove them. Essentially, all tight results for CSPs go through the long code, at least those that we know. So can we get that? So we can get almost tight results. And here's the statement. So for every epsilon, as small as you want, there is some value delta, and there is some CSP predicate, for which it is known that it's NP hard to distinguish between the case that it is satisfiable and the case that it is 1 minus delta satisfiable. This is known, and this is known to be tight, in the sense that there is an algorithm that does this, and doing anything better is NP hard. And for which we can get this universal hardness with preprocessing of the gap of distinguishing between something satisfiable and something like 1 minus epsilon delta. A small change for that. So the order of quantifiers, you first have to give me epsilon, and then I'll give you this delta. How does the proof work? So as a hint, we don't need for this the long code at all. So the proof, I find it quite surprising. So it's really an observation that just if you know that 3SAT, let's say, is hard to approximate within 99%, this already implies by a elementary reduction, nothing complicated, no long codes or anything, that for certain problems, really for k-SAT, for large enough k, in fact, you have essentially tight hardness of approximation results. There's an elementary connection between 3SAT and k-SAT when k is very large. And moreover, this connection works also in our setting with preprocessing. So because it's so simple, this connection, I don't want to show the proof. So like, it would be interesting to see. So really you don't, the proof is quite elementary. But I never know if things are elementary only as an afterthought or were elementary before you do them. So just try to think of it and see if you see such a reduction. Okay. So to summarize, like the research agenda that we have here is that of universal factor graphs, which is the same as preprocessing. So you get first the factor graph, you're allowed to preprocess it, and then you get the polarities. So in our preliminary results that we have so far, we managed to adapt some of the previous results to the new setting, and we see where the difficulties are in adapting other results. And we make some progress towards obtaining tight results. What are the open problems? So there are many open problems that I think, that I can think of. One I think is interesting is the following. Let's say you get the factor graph in advance, let's say for 3SAT. You're allowed to preprocess it for however long you want, and then you get the polarities. Can you now decide whether the instance is satisfiable or not in times rather than, let's say, the best running time, which is known now? Do it in somewhat smaller running time, let's say 2 to the n over 10. Can you do that, yes or no? Does preprocessing help at all? The same thing with approximation ratios. Is 7/8 an approximation threshold also with preprocessing, or does preprocessing help in any way at all? More generally, show even one CSP for which we have a tight threshold. So the result I showed before was not a tight threshold because of the order of quantifiers. We first had to fix epsilon, and then we said for large enough k that depends on epsilon, we had this tight result, but we would like to reverse the order, to say that, let's say for k-SAT, when k is 10, for every epsilon, you cannot do an approximation ratio better than 1 minus 2 to the minus 10 plus this small epsilon. The other direction is like, is there any CSP at all where preprocessing can improve the worst case approximation ratio? We don't know. More on the long-range goal or the greater picture. So this is something that partly motivated this research, and we don't know the answer. Are the universal factor graphs for unique games? Or in a sense, is the unique games conjecture only about understanding the factor graph? There's some evidence that connects between unique games and graph problems, specifically the problem of small set expansion. That was this connection was discussed by Raghavendra and Steurer. It's still not quite what we want, because it's like a reduction between these two problems. But we know that every constraint satisfaction problem can be reduced to a graph problem. That's not the question. It's not the same question. Like all NP-complete problems are equivalent. But this does suggest that maybe the unique games conjecture is not so much about polarities and things like that, but could be just about the graph structure. And the other question, which I think would be the most interesting one, is how do universal factor graphs look like? And can the knowledge of their structure help us in understanding NP hardness in general, or NP easiness? That would be even better. Okay, so thanks.
So what do you believe in the first one?
I don't know if I believe that the unique games conjecture is true, so it's hard to say what I believe. But, I think we'll do our best to find out and see what happens.
So I guess have you developed any intuition for what kind of problems preprocessing helps? Right? So I mean, it seems like what's working to help some lattice is sort of conjecture. You can gain constraint satisfaction problems, but for general CSPs, it maybe doesn't.
Yeah, so the result that we were trying to prove is really the 7/8 hardness, and we couldn't prove it, and I don't know if there's like a good reason why we couldn't prove it, because maybe preprocessing helps.
So you even injected into the preprocessing to help the general CSPs.
So there is only this case of these random CSPs at a certain densities, where there I know that if I had preprocessing, I could do more than without.
That's my exact question. Is there any, do we have a sense for characteristics of problems where it helps versus doesn't help?
So one thing that I was wondering is something like two-line linear equations with two variables. So this is really a graph structure. If you look at related problems, so max cut is very much related to it, but of course if you know the graph in advance, you solve max cut. There's no problem there. So the question is that with every two-line instance, there's a graph that is related to it, and somehow maybe max cut in this graph relates to what you can do in two-line. Maybe if you do some preprocessing, find these large cuts in the graph, maybe somehow it will help.
It seems to be something about sort of the expressiveness of variables.
Yes. Yeah. It seems so. So yeah. So this is the. I would say it's more likely that in fact you can recover all the thresholds in this setting, but I don't know. And also I should say that for the lattice and coding problems, there still is a gap also there between what one can do with preprocessing and without. It may change something.
More questions for Uri?
So many of the questions that you asked were to distinguish satisfiable from some constant away from satisfiable. But maybe some of those questions were simple answers because one answer is satisfiable. Maybe say.
Yes. So that's true. So for example, let's say for 3-sub, if you want to prove the 7/8, one way to do it, if we don't want perfect completeness, is to prove for 3 XOR the ratio of half, and then there's a reduction that would give the 7/8, but without perfect completeness. And this may be a bit easier. We tried to look at it as well, but couldn't do this as well. But it could help. You are right. It may be easier to do that.
and we try to do introducing from unique games.
So unique games, okay, so the question is, what do you believe about unique games? Do they have universal factor graphs at all?
No.
So one thing, for special instances of unique games, let's say linear, let's say 2-lin, we know that they have universal factor graphs in the sense that it is APX hard. These instances are APX hard, but the gaps are very small. So we don't have, for unique games, like a plausible starting point. Like, so of course we don't know that unique games are hard, but so we may like try both to assume that they're hard and that they're hard on some universal factor graphs and go on from there. But that's already too many assumptions.
That's very good.